Listen closely. A ship sank off a rocky Greek island more than 2,000 years ago. Divers found it by accident in 1900 hunting sponges, not history. They pulled up bronze statues, marble torsos, and a lump of green corrosion that looked like a stone with teeth. In 1901, when the lump cracked, museum staff saw bronze gears inside. A wheel. Another. Something impossible for the date stamped by rust and encrusted shells. They called it the Antikythera mechanism after the island near the wreck. For decades, it sat in drawers as a curiosity, a tangle of fused plates and gear teeth too damaged to understand. Scholars guessed. A calendar, an astrolabe, a toy. The truth took patience, new tools, and people willing to look past the corrosion and treat the object like a machine with a plan. Start with what the divers found. The cargo came from a big merchant ship that sank around the 1st century BCE, loaded with art likely bound for Rome. Among it were at least 89 fragments of a single instrument. The largest piece showed a bronze gear about the size of a cookie. Other fragments showed inscriptions in Greek, cramped and technical. No one expected fine gearing in the Hellenistic world. That bias slowed everything down. In the 1950s and 60s, a historian of science, Derek de Sola Price, took the first modern swing. He X-rayed the fragments, counted tooth patterns, and proposed that the device tracked celestial cycles. In 1974, he published Gears from the Greeks, arguing that the mechanism predicted motions of the sun and moon and perhaps the planets. He sketched a gear train that could turn a single crank into multiple linked rotations with specific ratios. It was a bold picture built on limited images. Then model makers and engineers stepped in. Michael Wright, an engineer at the Science Museum in London, studied the gear teeth closely and built working reconstructions. He argued the mechanism used epicyclic gearing and a clever pin-and-slot device to model the moon's odd speed across the sky. His models showed a moon pointer that speeds up and slows down just as the real moon does, because its orbit is not a perfect circle. That detail matters. It proves the machine was not a simple clockwork gimmick. It shows design tied to observation. It shows that theory about the moon's motion had been translated into moving parts. Wright also suggested a layered gear cage with coaxial shafts turning at related rates to drive several hands at once. The result was not a toy. It was a compact, teachable sky. The breakthrough came with new eyes. In the mid-2000s, a team from Greece and the United Kingdom formed the Antikythera Mechanism Research Project. They brought high-resolution X-ray computed tomography and raking light imaging. Layer by layer, they read hidden inscriptions and tooth counts buried inside the metal. The fragments yielded a dense user manual on the surfaces and a tighter census of gears within. The picture snapped into focus. The mechanism had at least 30 bronze gear wheels. It lived in a wooden case, roughly the size of a thick book, with doors that carried text. On the front, a large dial showed the zodiac and a Greek calendar ring. One pointer tracked the sun, another tracked the moon, and even showed its phase with a little half-silvered ball. On the back were 2 spiral dials. The upper spiral had 235 cells, the Metonic cycle, 19 years equal to 235 synodic months, a key rhythm for calendars. A small subsidiary dial counted 4 Metonic cycles to make 1 Callippic cycle. The lower spiral carried 223 cells, the Saros cycle for predicting eclipses, with notes about type and direction. A tiny 3-turn counter, the Exeligmos, kept time across 3 Saros cycles to refine the hour of future eclipses. Those back dials make the purpose plain. Turn the crank, set a date, and the machine tells you when and where eclipses are likely, what kind of eclipse to expect, and whether it will happen in the north or south. The inscriptions next to the Saros cells mention nodal crossings and even color notes for some eclipses. The front may also have carried a parapegma, a star calendar that lists when bright stars rise or set at dawn. The device is not a magic box. It is a compact, didactic model of the sky, as Greeks understood it, orderly, mathematical, and useful. One detail stands out. The lunar pointer's uneven speed likely came from a pin and slot that turns uniform input into variable output. That mechanism models what we call lunar anomaly. Greek astronomers, especially Hipparchus of Rhodes in the 2nd century BCE, describe the moon's variable speed with geometrical schemes. The Antikythera mechanism seems to embody that math in bronze. This is theory made tangible. Where did it come from? Inscriptions use month names linked to a Corinthian calendar. Other clues point to roads and the tradition of mechanical devices credited to Archimedes and later to Posidonius. The Rex date and the letter forms fit late Hellenistic craftsmanship. No maker's signature survives. The workmanship, tooth counts, and the complexity argue for a workshop, not a one-off miracle. Someone taught someone else to cut fine gears and to think in cycles and ratios. What about the planets? Price thought the planets might have been included. Later, researchers found textual hints of Venus and possibly Saturn in the surviving inscriptions, but no surviving planet gears. Some reconstructions propose trains for all 5 known planets based on Greek period relations. Others caution that the evidence for planetary pointers is partial. What is certain is that the sun and moon were tracked, lunar phase was modeled, and the eclipse cycles were computed on the back plates using neatly engraved spirals and precise pointers that step month by month. Call it what it is, the earliest known geared calculator that predicts astronomical phenomena. That phrase matters. A calculator, because you input a date and read off results. Analog, because it uses continuous rotation and ratios, not digits. Predictive, because it tells you about future eclipses and phases, not just current positions. Nothing else of this sophistication survives from antiquity. Why was it lost? Because most machines vanish when ships sink, fires burn, and metal gets melted down. Because later makers shifted to other forms, like astrolabes and armillary spheres, and then to medieval clockworks. Because technology is a chain, not a staircase. One link can break without erasing the knowledge everywhere. Islamic astronomers and instrument makers later built beautiful geared devices. Medieval Europe developed weight-driven clocks. The Antikythera mechanism shows that fine gearing was present long before those clocks, and that it served ideas not only timekeeping. Now look closely at what it teaches. The back spirals are not just pretty, they are data structures. A single pointer follows a spiral track across dozens of cells, each cell tied to a month in a cycle with notes about eclipses. That arrangement is a clever way to store periodic information using minimal space. The front dial's calendar ring likely had a mechanism to adjust for the mismatch between the lunar and solar year. The machine is not only a map of the sky, it is a tutorial about cycles, intercalation, and prediction. Think about the user. A scholar or navigator sets the date by turning a side knob. As the shafts turn, gear ratios translate a year of motion into months and days, into lunar phase, into eclipse warnings, into Olympic Games. Yes, games. Inscriptions mention the schedule of major Greek games. The same device that tells you when the moon will darken also tells you when the torch will be lit in Olympia. Calendar life and celestial pattern share a frame. The gear teeth themselves speak. Tooth counts match known astronomical periods. Ratios like 53 to 224 appear, linked to lunar anomaly schemes. The pin and slot offset reproduces the moon's varying speed. If someone faked this in the modern era, they would have to know ancient Greek calendars, eclipse cycles, and Hellenistic kinematics, and then cast a device in a way that perfectly imitates centuries of corrosion. The simpler answer is the right one. It is real, and it is exactly as old as the wreck that carried it. There is drama in the fragments too. Conservators found letters so small they needed special light to read them. The inscriptions read like a manual. At this month, in this direction, an eclipse. Names of months, names of games, mentions of specific cycles. The text density suggests a user who could read technical Greek and who wanted the device for practical teaching or planning. This was not a palace toy. It was a working instrument. What did it change? It forced historians to redraw the timeline of precision engineering. Before it, many assumed complex gearing arrived with medieval clockmakers. After it, no one could hold that line. It also reshaped how we read ancient science texts. When Hipparchus describes the moon's motion, we now see a path to metal. When we see Babylonian period relations borrowed and translated into Greek geometry, we see how numbers became gears. The story also warns us about gaps. We have one shipwreck, one device in fragments, and a few ancient references to geared spheres and planetary models that no longer exist. It is dangerous to overgeneralize from a single survivor, but it is just as wrong to ignore what that survivor proves. People in the Hellenistic world built machines that encoded the heavens with precision. That fact stands whether we find 5 more or none. The search continues. Modern teams dive the wreck site with better gear and have recovered more finds from the ship, including statues and hull pieces, but no complete second mechanism. Imaging keeps improving. Scholars keep refining readings of the text. Each new letter helps. Gear modelers test alternative trains that satisfy the counts we have. The work is slow because the fragments are fragile and because caution is the right speed when history can tilt on one misread tooth. There is beauty in the method. Start with what is measured: tooth counts, letter forms, track layouts. Build a model that matches those constraints. Turn the virtual crank and see if the outputs land on known cycles on the right dates. Compare to the inscriptions. If the model misses, notate the miss and try again. The process mirrors the device itself, a cycle of hypothesis, rotation, and readout. Now place the mechanism back into human life. Imagine a scholar in Rhodes unwrapping a freshly made instrument. The wood case smells of resin, the bronze shines. He demonstrates. Turn the knob. The sun hand moves through the zodiac. The moon hand slips ahead and lags, the little phase ball shading from black to white. On the back, the pointer advances one cell in the Saros spiral, and the side dial ticks the Exeligmos. He explains to students why some years bring more eclipses than others, and why certain alignments repeat with a cadence you can plan around. You can feel the lost continuity too. If more devices like this had survived, the standard story of technology would list Greek-geared calculators as a living tradition, not a one-off flare. Instead, we got a broken transmission, revival elsewhere, and the long arc to modern clocks and orreries. The Antikythera mechanism shows that progress is not a straight line. It is a network with missing bridges. What remains today sits in a museum case in Athens, in pieces that look like dark coral with teeth. Next to them stand reconstructions that turn and whisper. You do not need to romanticize it. The device is already romantic in the honest sense. A working model of the sky, built by people who believed numbers could be made to move. That faith is the engine under every lab bench and in every code repository now. Here is the simple claim you can carry out of this story. Ancient engineers built a portable machine that uses geared ratios to model lunar and solar cycles, predict eclipses on a 19-year and 18-year rhythm, track lunar phase with a mechanical trick that encodes an astronomical theory, and tie civic calendars and games to those rhythms. It is the earliest known analog computer. It is not an outlier in brilliance. It is a surviving page from a chapter we mostly lost. If you want a final lesson, take this. Artifacts seldom speak on first look. You get answers when you add light, rotate, and try to read past what time did to the surface. The Antikythera mechanism was not solved by a single genius with a hunch. It was solved by repeated, disciplined looking, by people who took ugly data and gave it context. A shipwreck tried to turn a machine into a rock. Patient minds turned it back into a machine. It rewards patience and clear eyes and honest doubt. And in that reversal, a piece of the ancient sky started moving again.